just so happens that tomorrow is Valentine's Day. So I have some Valentine's numbers for you, a little trivia for you to start things off. For example, they estimate that this Valentine's 180 million cards are going to get exchanged. But interesting, they said 61% of consumers participate in this holiday and the other ones don't. So a good 39% are saying, oh, I'm not going to bother with it. But the average spending is $101 per person that participates for a total of $13.7 billion spent on Valentine's Day tomorrow. Okay, and just in case you're curious, approximately 214 million red roses will be produced for tomorrow. Crazy, huh? Well, I do have a little math from the real world for you. I like to show you, some math you might not see in a math class or something that you might encounter in your day-to-day life. So today we have a little Valentine's math problem for you. I can't quite say it's the real world, it's the animated world, but we have a little confrontation between Milhouse and Lisa here. See, Milhouse has liked Lisa Simpson for a long, long time, and he's had a little trouble getting her attention. So as the story from Valentine's goes, we have here Milhouse playing Cupid, and if Cupid can get his arrow on Lisa, well, then we're going to have a love connection, and Lisa will follow him home, and they'll live happily ever after. But if you look at my illustration, Milhouse does not have very good aim. In fact, he's not hitting Lisa at all. He's either going too high or too low, and he's hitting squirrels and deer, and they're following him home instead of Lisa. So we are going to help Milhouse out. And so, yes, this isn't quite the real world, I realize, with Cupid's arrows, but the mathematics actually is. So this is just an example of what's called projectile motion, and I have a couple of equations for you. I'll show you. So we're going to take Milhouse out of there. Here's some equations for you. These are standard equations, and if you'll notice, actually I'm giving you two equations because we're going to look at the x and y values separately. So there are some shorter equations to use, but actually this is kind of a nice way to look at it. And one thing I want you to realize is before we do that, I have a little illustration on my computer. You can look exactly what we're going to try and do here. I have the path of the arrow drawn on my computer here for different angles, and what I want you to notice is look at the shape of the graph. It's a nice little parabola. So this little red dot is Lisa here. Sorry, Lisa. I should have made you look a little better than that. But if you want to hit Lisa, basically we just need to make the angle correctly. And if you notice, it is a nice parabola. So if you've had an algebra class, you can actually study these equations. They're just based on x squared. So if we change the angle, you can see we might have a chance of actually hitting Lisa just right, somewhere around there. So we are going to figure this out. If you go back and look at my equations, these guys, I gave you two separate ones. I need to give you a little more room here. Hold on. There we go. If you notice, they both start out with some variables here. The v is the initial speed, and for our little problem, I'm going to pick a typical speed of an arrow coming out of a bow. We'll say it's 200. So it's going to be 200 feet per second. The angle here is represented by theta. That's your initial angle that you're going to, aim your arrow at to try and get your target. And you'll see an extra piece on the y value. This is accounting for gravity. So we have the initial velocity pushing this arrow in both the x and y directions, and we're accounting for that with some trig functions. And then the letter t is time, and this g here is gravity, and that is 32 feet per second squared. That is known. So I basically have a set of equations here, and we're going to try and figure out how to make our arrow hit Lisa. And I made a couple assumptions. We're going to say Lisa's 800 feet away on nice level ground. And we know the speed here, and all we got to do is figure out what angle poor Milhouse should use to make this happen. So look what our equations become. The x value is 200 times cosine of the angle, so we have a little trig there, t, and the y value is 200. It'll be sine theta t. It looks very similar, but then minus, if you put 32 in for our gravity, it's 16t squared. So now you're going to think about, okay, if I put Milhouse at the origin, which I did on my graph on my computer, what do we need to get to make sure we hit Lisa? And Lisa's going to be standing 800 feet away. So Lisa is sitting at the point 800, 0. So all I really need to do is make sure that I make my x value equal to 800 and the y value 0, and we'll see what angle we actually need to make this happen. Okay, ready? So I'm going to take my x value. We need the x value to be exactly 800. So I'm going to actually solve this. This is 200 cosine theta times t has to be 800. So what I'm going to do is I'm going to solve for t and get a little expression there, and then we'll put that in the other equation, and then we can actually solve and we'll get a number for our angle. All right, here we go. I'm just going to move things around a little bit. So I've got 800 over 200 cosine theta, and I'll reduce that. It's just 4 over cosine theta. And that's equivalent to t. This is the time at which we would reach our target, if you will. I'm going to place that in the second equation so we can see what's going to happen here. So second equation, now the y value, remember I want to hit Lisa, so this is going to be 0. So instead of y, I'm going to put 0. You can see the equation right up top. 200 sine theta. Instead of t, I'm going to put the 4 cosine theta minus 16. And again, instead of t, cosine theta. So I'm going to speed through a couple little simplifications for you just so you can see what's going to happen here. For example, this will become 800 sine over cosine. And the next one is minus 256 over cosine squared. We're going to actually solve this and see what kind of number we get. So a little trick here, so a little algebra practice. I'm going to multiply both sides by cosine squared. So multiply by cosine squared, and that will create 0 on the left, 800 sine theta cosine theta on the right, minus 256. All right, it's getting a little easier. Let's see what we have left. I have 800 sine theta cosine theta, little trig for you, equals 256. All right, I'm going to do one last thing. If you had a little trig class, I want you to see if this looks familiar at all. I'm going to divide both sides by 400. Why 400, you ask? Why not 800? Why wouldn't I just get rid of the 800? Well, I want to leave a 2 there on purpose, and I'll show you why. This would become, this reduces, I think. We'll put it like this for now. This is an identity. There's a trig identity that makes this simpler, and if it looks familiar to you, if you had a trig class, it should look familiar to you, even if you don't quite remember it. That is the sine of 2 theta. And actually this does reduce. I think this becomes 16 over 25. So a little trig formula for you to solve. If you go on a calculator, you can go backwards through that trig function and actually figure out what the angle is. So 2 theta would be the inverse sine of 16 over 25. I did it on a calculator. It came out to be 39.8. That is 2 times your angle, so I'll divide by 2. Our angle is about 19.9. Well, 2 things. I will show you real quick on my computer that that's actually about right, because I have the angles marked on my computer. So we're going to go at about 19 degrees and see if we can actually hit Lisa. And I don't know if you can see the number at the very bottom. It's a little small, but about 19 really does hit her. I want to show you one other thing, though. We can actually do it another way. There's another answer. So we can actually hit her by shooting the arrow really high at an angle of about 70 degrees, and it'll come all the way back down and get her just right. So if you've had a little trig, you can ask yourself, how come there's another answer? How could I find it? And the key is looking back at this little equation right here and saying, hey, there's another solution to this. There's actually a whole bunch of solutions, and 2 of them pan out to be actually useful for our poor little Milhouse. All right, so Milhouse, I hope you get your Lisa. For the rest of you guys tomorrow, if you're celebrating or not, well, I hope you have a good day on Valentine's Day, whatever you choose to do. My poor students have a test, so they're probably not happy with me. So any excuse here in the studio to celebrate? Well, there are crazy traditions with St. Patrick's Day, right? You're supposed to wear green, maybe wear a crazy wig. If you don't wear green on the day, it's Monday, you get pinched. You can eat corned beef and cabbage. You can drink lots of green beer. And, well, I have a couple things on my computer I'll show you. You can, they have a big thing about shamrocks. You can wear a shirt with a shamrock on it. Or if you're really lucky, you can get a 4-leaf clover, which is technically not a shamrock, but they're supposed to be good luck, right? About a 1 in 10,000 chance, by the way, of finding one of those out in the wild. Or you can go to Chicago and they actually dye their river green, believe it or not. Or you can go by some old folklore and try and look for a pot of gold at the end of a rainbow left by the leprechauns or guarded by the leprechauns. All these crazy old stories, traditions. Well, I couldn't find any good math for a leprechaun, so I'm going to show you some math involved in rainbows, actually. And there's a lot more math than you might have thought. So for starters, we're going to figure out how these rainbows show up and why they make all those nice colors for you that they do. The first thing I have to show you, though, is what happens when light hits water, because this is the key to how these rainbows are formed. So on my little math cam, I have a little simple diagram. We have a water level here, and we have this is a ray of sunlight here, and the sun's going to come right in the water. What happens when the sunlight hits the water? Well, it doesn't continue through at the same angle, actually. Once it hits the water, it actually changes the angle. And let's say you're down here swimming, and you're looking up. The light that's hitting your eyeballs is not coming right down from the air at this angle. It actually changes. And in fact, it's a little calculus problem to figure this out, and I thought we wouldn't do it here because it's a little bit involved, but I'll give you the idea of what you would do. And if you've had a calculus class, you might have actually done something like this in your own class. It's just an optimization problem. What you would do is make little triangles here, and you would measure these distances. For example, you could call this x. It turns out that light always travels the fastest way possible, and light happens to go a little bit slower in water. So that's why it has to change its angle to get there the fastest. If it needs to get to your eyeballs, which is what we're hoping, right? It goes a little longer in the air, a little shorter in the water, so it actually moves over a little bit, just so that it can have the fastest time possible to get to your eyeballs. And you can figure out exactly what point it hits at and exactly what angle it goes if you do some right triangles, some Pythagorean theorem, and set up a little formula for yourself. In calculus with a derivative, it'll tell you exactly where that point is, and you can figure out what angle it goes through. So they've studied all this. They know exactly what is called the refraction index of water is. They know what that angle is going to be. The next issue is, how does this light and these angles make a rainbow out of you? So next we have to look at our raindrop. So here is my sample raindrop. This is a perfect spherical raindrop, which, they're not usually perfect spheres, but it's okay for our purposes here. So what I want you to imagine is we're going to have this raindrop that's going to get hit by sunlight. And here's, roughly speaking, what happens. So the sunlight comes in like this, and it hits your raindrop, and it does not continue along the same path. Actually, some of it gets reflected, but some of it goes right through the drop, but it does get angled a little bit. So if that's the straight direction, it would actually get pushed in like this, and it'll hit the back of the raindrop. Well, again, the same kind of thing happens. Some of the light goes through the raindrop and just disappears behind it. Some of it actually bounces back. And when it bounces back, it has a nice symmetric angle it comes back at. It hits the edge of the raindrop. Some of it gets bounced back in, but some of it actually comes back out of the raindrop. And again, the angle changes a little bit. So it comes out at this angle, let's say. It gets pushed back at a slightly altered angle. So the sunlight is hitting these raindrops, it's bouncing around, and it comes back out of the raindrop at a different angle. And this angle here, the change that you actually see, is what we want to figure out if it's going to hit your eyeballs or not. So there's some kind of complicated equations we can do, but I'm going to show you, I put on my computer here a graph. Let me explain to you what this is. This is a graph, and the numbers are very small, I know, and you can see that crazy equation I set up for you already, so we don't have to do it live on the air here. But what happens is the x-axis is the angle that it hits the raindrop at, and the y-axis is the angle in relative to that it leaves at. And what I want you to notice is near the top here, you definitely have the largest angle that it changes. And the numbers are kind of small, you probably can't see it, but it's about 42 degrees that you actually get this angle happening. And what I want to show you on why you see the rainbow, I'm going to put this graph on my math cam here. So same picture for you. So look at the top of that graph. I said this is a y value of about 42 degrees here. That's about right. Well, if you'll notice that near the top of that, there is a concentration of values in a sense that for a fairly big span around that number, let's say about this much, all these inputs here, so all these angles that are coming into your raindrop are giving you roughly the same value output. So it's roughly the same angle that you're seeing. So all these values, if you map them up to here, they're all going in a pretty narrow value up here. So you have a lot of angles coming in that will give you a similar angle coming out. And that doesn't happen at the other possibilities where it hits your raindrop. So what that means for us is that there's a concentration of the rays. There are more rays in one exit angle than others. And that angle is about 42 degrees. And that is the angle that you actually see with your eyes. So the truth is there are, all the drops all over the air are all reflecting light all over the place. It's just that you happen to see a concentration in one particular area. So I'll draw you a little picture here what's going on. If you're watching a rainbow, you're standing here on the ground, the rainbow you would actually see would be sort of ahead of you over here. And the center of the rainbow, if you can imagine being a complete circle, is always opposite the sun behind you. So the sun actually has to be behind you to make this happen. I don't know if you ever noticed that before. And the center of the rainbow would be just directly across from the sun, and the light rays come in, they make all these reflections, but the concentrated ones are at this sort of magic 42 degree angle, and that's exactly what you would see looking up at a rainbow. So when you're looking up at a rainbow, you're looking at about a 42 degree angle to see these things. All right, next issue. How come they're different colors? I mean, what we all just explained here is the light gets concentrated, so you can say, all right, fine. You should just see maybe, a big bright white light in some area of the sky, but you actually see all these nice colors. Well, the reason you see that is because the rays of light are actually different colors, and the different colors have different wavelengths, just a little bit. And what that means is they bounce off at different angles. So I'll show you a couple pictures on my computer here. I have, for example, a couple nice rainbows to show you. This is a nice large arc here. And then this is a really intense image. I hope it's real. I think it is, where you can see the rainbow just landing right in the middle of the forest. You know, that's where your pot of gold should be, right? And then here you have a nice rainbow image actually coming up from just the spray of an ocean wave. And so again, this is all reflections off the water droplets, but what you need to understand is how come you're getting all these crazy colors. And if you want to look at a little diagram here, this is the light rays coming in, and the different wavelengths are bouncing at slightly different angles. So this is what creates the colors for us. Actually, the red is about a 42-degree angle. The blue on the other end of the rainbow, the blue and the violet, there's a slightly different wavelength, and so the angle that it bounces off the raindrop is a little different. So you see the blue at the other end of the rainbow, and all together it's a span of about 40 to 42 degrees. So looking up at the sky, you know, the rainbow is roughly a 2-degree difference. So that's actually what you see. You just see reflections. Now here's a couple things to think about. This is weird. Your rainbow is never the same as somebody else's rainbow, because the rainbow is not sitting in some fixed location. You can't go drive to the rainbow. You can't drive under it. Sadly, you can't find the end of it to find your pot of gold or Skittles, whatever you're looking for. It's impossible. As you move, the rainbow will move as well, because it's just a reflection. It's an illusion. So you're seeing the rainbow reflecting just perfectly to hit your eyes at exactly your position and then get just the right angles. If someone's standing next to you, they're seeing a slightly different rainbow. And the colors you see are because those angles are stacked just perfectly. So I mean, in a sense, there's raindrops reflecting blue all over the place, but you just happen to be seeing the ones that are at that concentrated angle we talked about. And the raindrops below that you're letting you see another color that's concentrated at your eye level. So you see all these nice colors. Now if you're really lucky, this is really lucky, you can sometimes see a double rainbow. I'll show you a picture of one. I brought some with me. This is a nice image. You can see a sort of fainter rainbow behind it there. There's a nice strong rainbow in the front. And then I have one more of a complete arc. You can see a more faint one, but above it you see a double rainbow there. That is because you can have more complex reflections happening inside your raindrops that create a secondary illusion there. And other weird things can happen, like if you're in an airplane, you can actually see a perfect round rainbow all the way around. We normally can't see that because it runs into the earth and you can't see the rest. So anyway, next time you see a rainbow, don't go looking for pots of gold or leprechauns. Just remember, you're really seeing reflections, and all the math we talked about, all the angles are creating those nice, pretty colors for you. Hey, it's Mathman Dan here. We're out in the real world, seeing where math shows up, and hey, we're at SeaWorld. What could be better than that? I'm here with Jennifer. She's a civil engineer for SeaWorld, which is a pretty cool job. So obviously you have lots of math involved in engineering, but what ride are we standing in front of right now?
This is our Shipwreck Rapids ride.
So you were telling me a little bit of the mathematics that went into the engineering of this ride. So for example, how do they create the rapids when you're going through and getting all wet?
Right, so the trails that the actual raft travels in has different slopes and different platforms in the bottom base of it to create those rapids and those thrills. So when you're going through and you see the splashes come up and over, those are actually planned all throughout the ride.
So you look at the design of the trough, if you will, that it's going through, and you can sort of force the water the way you want it to go.
Exactly.
And make all the splashes for people.
Exactly.
I've seen them come off very wet, so. All right, well, what most interests me about this ride is this device behind us, which is called an Archimedes screw.
Correct.
This is basically pumping water uphill, right?
Yes.
So what can you tell us about this thing?
These screws are 40 feet long and they're 10 feet in diameter, and they pump the water from an elevation up to 12 feet higher than the existing elevation. It moves about 46,000 gallons a minute of water up that 12 feet.
Just this one screw?
Just the one screw. So when you put the two screws together, that amounts to 92,000 gallons per minute, which is equivalent to about 4 residential swimming pools. So it's a hefty amount of water that's moving up.
And is this more efficient than having a traditional pump, if you will?
Yes, it is. And it's actually, it dates back to BC times when mathematicians and scientists first discovered the use of this screw. And so the efficiency to irrigate the lands back then, they needed to find efficient ways, and this was one of the things they came up with.
So I actually read this was invented over 2,000 years ago, and it's amazing. And you guys are basically, you're using a powered version, but it's basically the same idea, exact same design.
Exactly, yes. SeaWorld San Diego was the first to use this Archimedes screw design in the amusement park ride itself.
Oh,
so
right?
we're very proud of that fact. Yeah.
Well, I was very impressed looking at it, and I did a little homework on it, and I know that for the math involved, aside from just the way it works, you have to get certain angles for it to be able to push the water uphill.
Yes.
Otherwise it doesn't work.
Yes.
And depending on how many fins you have going around and the radius of those fins, depends on how fast it can go and how quickly it can push water up the hill.
Exactly.
So I was thinking we could look a little bit at that in the studio afterwards, but you also mentioned to me something mathematically about the outline of it if you look at it sideways.
If you look at it from its side profile view in its stopped position, it actually is two sinusoidal curves that are melded together. And so it's the sine curve itself that's actually moving the water up into the reservoir.
So you can almost imagine a sine wave moving and it just pushing the water right up with it.
Right.
Well, it's pretty cool to watch. I'm not going to go on the ride because I'm not going to get soaked, right?
Sure.
But Jennifer, thank you so much for your time today showing us
You're welcome.
part of your job here at SeaWorld. And back in the studio, I'll show you a little more about this Archimedes screw. It's pretty cool, actually. All right, that thing is pretty cool, actually. Now think about this. This is amazing that they thought of this over 2,000 years ago, and we are basically using the exact same design today. I mean, we have a powered version, but it's the same kind of thing. Now, a couple of things that we weren't mentioned when we were actually at SeaWorld. It's a very efficient way to transport water uphill, but also it has no problem if there's stuff in the water. Like, I mean, they actually use it at water reclamation plants, for example. And also, if you were actually working in an area that had live fish, the fish could get stuck in that screw and just go right up and it wouldn't hurt them at all. Unlike, there's a lot of the mechanical pumps we have now. Well, anyway, there's a couple things I was going to show you about this invention, and a couple photos first. So first of all, the culprit Archimedes. I have a picture of him, a representation anyway. So there's some debate whether he was actually the one that invented this or just the one that sort of made it more publicized. But anyway, I'll leave that to you guys to decide. But check this out. In Italy, they actually made a stamp of him. And hey, look what's in the background. There it is, the Archimedes screw, pumping some water right behind him. Now, I mentioned it's over 2,000 years old. This is a woodcut from the 1500s, so I know it doesn't back up my 2,000-year claim. But think about that. That's 500 years ago. They're actually making art prints out of these devices they were using. This is an example of one. I think this is in a museum somewhere or a science center somewhere. I kind of like this picture though because it's not enclosed by a tube, so you can actually see the coils and see how water might sit in there and kind of just truck it uphill. This is actually being used in Tennessee. This is part of a water plant, and they use it to pump water up. This is one in Holland, also used to pump what looks like kind of murky water there. But all right, and this, okay, look at this carefully. Apparently, you can use one of these to steal beer from your friend. Yeah, okay. Now, I know that seems crazy, right? But they look very serious about it, don't they? I suggest just wait till your friend isn't looking and grab the glass and just pour. But, maybe this makes you feel a little more mathematical or something. All right, so what's the math going on in here? Well, I'll show you a diagram in a second. But for one thing, the blades themselves, if you looked at what these things look like, it is like a big corkscrew. It's a mathematical shape called a helix. And it's a very common mathematical shape. It shows up actually in DNA molecules, for example. And if you go up through calculus classes, you'll see this used a lot as an example in some of the problems you'll learn there. We also mentioned slope because the screw itself has to be at certain slopes, otherwise it can't push the water up there. And the blades themselves have to satisfy certain slope requirements in order for the device to even work at all. Our friend, the civil engineer, she also mentioned that if you look at this from the side, it looks like sine waves. So I thought, let's see if she's actually right. So what I did is I got a diagram of these things, and then I actually graphed a sine wave using mathematical software, and I superimposed them. So right now, we are going to see if indeed this really is true. So I have a sine wave, that blue wave. I tilted it already for you, and we're going to slide this into place, and I want to see if it really does match up. And check this out. That looks pretty good. It really does match the shape by the helical fins, if you will. But also I want to show you there's another sine wave you can actually draw. She didn't mention this one, but if you look right in the middle there. Now on the center core, there's like an outer radius of the fins, but there's like an inside radius where the fins are attached. And if you look at that, there actually are more sine waves. I'll try and draw one here. I'm freehanding this, so it's not going to look the best, but there really are 2 different sine waves in there that you can picture. Now the deal is, I mentioned these slopes. This slope here, the blue one that I lined up, where it crosses over the center of the screw has to be a certain angle or a certain slope, or else it can't push the water. And so basically what I wanted to show you was, like, look right, let's say right about here, that spot I'm circling, right where it crosses the center there, that has to be a downhill slope here when it comes on the closed side. So as it turns, if that's not downhill, it's not going to push the water. So you have to have a negative slope at that spot. So there's a couple of things you could change. So for example, when they're designing these things, some more math to consider. They have to consider how many fins to use. They have to consider how tightly to spiral them, and then they have to figure how fast you can turn the thing to crank up a lot of water. And if you were listening to our friend at SeaWorld, she was telling you, I mean, it's like almost 100,000 gallons of water a minute between those 2 devices. That's an amazing amount of water they're doing every minute. So these are very powerful machines. Well, there's a guy in Drexel University. His name is Chris Rores, and he did a very, very thorough study of this exact story. So I'm not going to, we're not going to read this together, okay, because this is very detailed, but I will show you what we have here. This is his research paper, and he tried to figure out the best way to build one of these things, and there's tons of math in here. I'm just going to show you a couple of highlights, okay, because we're not going to read through it, but I'll tell you a couple things he mentions, and if you look through this document, you're going to see a lot of cool math. So he has a bunch of diagrams, for example, and then there's some really nice, there's a whole bunch of equations, for example, but there's some really nice 3D graphs. This is like something you would do in a Calculus 3 class, where you'd actually try and look at a function that has 2 inputs into it. He has several of these, so you can try and figure out what the different scenarios are. And then there's a whole bunch of calculus. See some integrals there where he's computing areas just like you guys would do in maybe a Calc 2 class if you go that high. So lots of good math here, some more graphs. So let's see, what are some of the highlights that I can tell you from here? Well, for one thing, you can't turn these things as fast as you want. They've determined that the speed you can turn them out is roughly 50 divided by the diameter to the 2/3 power. So if you figure that out, that's about how fast it can go. If you go faster than that, it kind of churns the water and it can't really scoop any of it up. Also, a couple other things I learned from this little paper. You do have to tilt it enough, as I mentioned. You have to get the slope just right. The outer radius, what he did was he assumed that the outer radius would be a certain amount for whatever application they wanted, and he assumed he'd use a certain number of blades, and he assumed you'd have the whole thing at a certain angle, and from there he tried to decide, well, how big should the inner core be, the inner radius, and how tight should the spirals be to make the very best, the most efficient machine, the most amount of water you can crank up there. And what he determined was, so I looked up our example from SeaWorld. I think SeaWorld had 3 helical blades on each of those things. And so according to his research here on this paper, and by the way, I'll put a link to this paper on the blog if you want to check it out. It's too much to read to you over the air, right? So he said that the inner radius should be about 54% of the outer radius, so actually slightly bigger than halfway out should be the inner core. And I looked at the footage from SeaWorld, looked about right. And also the spiraling should be about 22% of the widest spiraling you could possibly do. So the widest spiraling would be, so you just barely get that downhill slope of the blades that I mentioned. If you take the longest spiraling you could possibly do, you should make it 22% shorter. One interesting last tidbit, this Roman guy named Vitruvius in the 1st century BC actually wrote up a design of these things. He based it on a 3-4-5 Pythagorean right triangle, and he used 8 blades. And using those measurements, our researcher here checked it out, and he was within 7% of the right radius and 27% of the right spiral. So over 2,000 years ago, they're doing pretty good. A little fancy math, though, we can do even better.